Uh, I wanted to tell you about this, what I learned in this semester that Ernesto and Lino are organizing, and basically I'll follow the following plan. So first, I'll remind you about some packets from algebraic geometry. And by this I mean classical geometry. And then the new read of classical geometry through homological mirror symmetry, meaning through category theory. And then, so I'll very briefly mention the classical theory of Milnor. And then, so I'll give a new interpretation through category theory. And then finally, if the time permits, logical modular forms. And phantoms. So, in fact, this theory that I'll be talking about is was pretty much developed at the same time when Milnor was writing his examples of exotic seven spheres. So I am not sure if there was any discussion between Artin and Mumford and Milnor. I mean, maybe Philip knows, but it is the same phenomena that is actually happening, and I don't know if they have observed it or not. So let me start with the so-called Mumford-Artin example. So, I mean, there are many ways you can think about it. I mean, I'll propose to you a way which, I mean, I'm sure it was known before, but it was worked out in a paper that I wrote with Iliev and Kryzhelkovsky. So, this theory of atoms that is being developed and written up now actually comes out from this paper. And so the example that is explained in this paper is as follows. So you would like to realize the Brouwer group associated with some three-dimensional funnel in a geometric way. And how do you do this? Well, so there are P1 vibrations over a base which come from the projectivization of rank 2 bundles, and there are some P1 vibrations which are not projectivization of P1 bundles, and so these second ones are the ones that are connected with non-trivial elements in the corresponding Brouwer group. But how to geometrize this? I mean, you start with the two-dimensional, with the four-dimensional Grassmannian G24, and it contains, according to Rai, an Enriquez surface in it. And so you blow up this Grassmannian in this Enriquez surface. So let's denote this by blow up things by X. And this actually turned out to be a Q1 bundle. This over the open part over some Fano manifold. I'm sorry, about some three-dimensional manifold. And so, I mean, quick calculation of Amalford shows that this fundamental group of the Enriquez surface, that's true, but of the Enriquez surface, which is torsion, so actually factors in this construction after some modification blow up and smoothing of Z0. So you actually see that H3 of Z is Z2, and so there's a direct connection between these two. And then this variety happened to be precisely the classical Mumford-Artin example, and so that's why you conclude that Z is not rational. For the obvious reason that if it was rational, it was supposed to be obtained from P3 by blowing up and blowing down, but P3 doesn't have torsion in its H3, so this cannot be obtained in such a way. So this is once again this classical construction, which tells you that you can geometrize the non-trivial element in the Brouwer group, namely this Q1 bundle, which happened to be not obtained by projectivization of rank 2 bundle. And so this allows you to see this torsion element in the fundamental group of the Enriquez, produce a torsion element in H3 of this bundle. So now, this is approximately at the time where mirror symmetry entered the game. And so the point of this paper was to show that in fact, you could see this torsion on the so-called Landau-Ginzburg model, and it appears that the Landau-Ginzburg model in this situation is an orbifold, and so you can deform this orbifold, it becomes singular, and then you resolve the singularity, and so you actually, in such a way, create something which is called in conformal field theory discrete torsion. So it's a certain element of the K group of the corresponding category, which I'll mention in a second. So this approach is classical, but you can really categorize this approach and talk about it in terms of derived categories. And so there are many people who work on this. And so they study the derived category of Z. And so the Hodge diamond of Z looks like so. I think it's something like that. And then this derived category has the same orthogonal decomposition of derived category of an request surface, and then you have so you have 12 other exceptional objects. Yeah, that's right. So now it is rather clear that this DBZ cannot be a rational thing, because so in fact the piece that corresponds to the derived category of the request is precisely this part. So it's 1, then 10, 1, and then 1. And so you have a piece which corresponds to a surface, and it's well known that in dimension 3, the things that you can obtain are either points or curves. So if you really have a surface in this semi-orthogonal decomposition, this cannot be rational. And so this observation, which so I mean, there are certainly Kuznetsov is the main person here, but there are other people like Sono, Perry, and those that study this thing. So you see that derived category also tell you that this cannot be rational, but you can even see this on level of cohomology. So you have this splitting of the Hodge diamond on so this piece, and then 12 other pieces. And so this splitting of the Hodge diamond is canonical. And since this Hodge block cannot come from a Riemann surface, it cannot come from a point, so that's why you know that in many other ways that this three-dimensional funnel is not rational. So now what I would like to point out to you is that really what is happening here is this is some version of the so-called Brouwer-Severi varieties. And so Brouwer-Severi varieties are varieties which are forms of Pn, but then they don't have any points over a given field. So these are PNs, but without points over this field. And there is a big theory of these Brouwer-Severi varieties. And so different Brouwer-Severi varieties are based, so Brouwer-Severi varieties, but also you can consider Brouwer-Severi schemes. Over X. And so these are actually classified by the homology of certain homology with coefficients in C star over this scheme X. So Brouwer-Severi varieties are the varieties which are forms of Pn, so they are just Pn over some field K, but they don't have, this Pn doesn't have a point over this field. And the same thing is true for Brouwer-Severi schemes, so which are family of Pn's over certain base X, but these schemes do not have, so these fibers do not have points over these schemes, sorry, over these fields. And in other words, you don't have a section of points of this Pn's over the base X. So now, I mean, obviously, if you don't have a point over this field, so this cannot be the classical Pn. So therefore, you cannot talk about rationality because rational varieties usually have a lot of points. And so seeing in the derived category some kind of shadow of a Brouwer-Severi variety, also of Brouwer-Severi schemes, could be exactly shadow of non-rationality. And that's exactly what's happening here. So you have this P1 vibration, which in a way is Brouwer-Severi scheme over this base, Z0, and but it doesn't come from projectivization, therefore it's connected with the non-trivial element in the Brouwer group, which in this case happens to be precisely Z2. So that's the whole point in this observation of Mumford and Arthur. So just to repeat once more, that we start with this Grassmannian, which is obviously a rational variety. We blow it up in Enrico's surface, and then we consider another vibration over by P1 over a base, and then so this vibration happens to be corresponding to non-trivial P1 bundle, meaning a bundle which doesn't come from projectivization of around 2 bundles. That's why this element corresponds to the non-trivial element of the Brouwer group of Z, which happens to be Z2. And so basically, the non-rationality of Z is connected with the fact that this vibration comes from non-trivial Brouwer-Severi scheme in this case. So now, what I would like to notice is that there is an important ingredient of this construction, and that is, which we'll explore, and that is what was known very classically, that this Enriquez actually is a surface which is obtained by log transform from P2 blown up at 9 points. So in other words, you start with P2, you consider two elliptic curves, namely three smooth curves of degree 3. They intersect at 9 points, which you blow up, and that gives you a vibration over P1 with fiber and elliptic curve and 12 singular fibers. So now you choose two smooth fibers, and then what you do is you do a surgery, which means that you take a small neighborhood around this point, so the base is disk, and then over each you have smooth elliptic surfaces, sorry, elliptic curves, and then you glue back this thing after a dent twist, and so obviously this P2 blown up at 9 points has trivial fundamental group, but this dent twists are further 2. In both of these points, you actually do create a fundamental group, and this elliptic surface with these two, then with these log transforms is so the main thing which transformed this elliptic surface from the rational one is this surgery that is happening here, and that is going to be something which we'll be exploring quite a bit in our considerations. And then the last thing that I want to mention in this construction is that there is some very funny category working in here. So in particular, this could be split further. It's different from this splitting to semi-orthogonal decomposition of a category alpha, and then another uh, 12 exceptional objects. But this category is a funny one, and it has K0, which is precisely equal to Z2, but it has trivial Hochschild homology. So it's a non-trivial category, but with trivial Hochschild homology. And so such a categories were conjectured to exist by me, but they eventually proven to exist, and they are called quasi-phantoms. So, so it was conjectured a long time ago by Bondo that they don't exist in the geometric case, but this turned out to be a wrong conjecture. So they pretty much are everywhere, even in the case of rational surfaces. So, so that is the categorical invariant, which actually will play the role of Kerber-Milnor invariant for the Milnor spheres that we want to consider. All right, so this is the part of algebraic geometry that I wanted to mention. Just one thing, that derived categories of this Brouwer-Severi schemes are very well understood. And so if you have a Brouwer-Severi scheme over X, and X has an exceptional collection, then, so let me denote this by BSS over X. So the derived category of BSS over X is equal to the semi-orthogonal decompositions of different derived categories. So, but these are not derived categories of complexes, but derived category of shifted complexes. and it has exactly as many derived category of shift complexes as many are the exceptional objects in this base of X. So, I mean, it's all of these things cannot be rational. They are not connected with. They are twisted complexes. They cannot be connected to anything to the usual algebraic variety. So, appearance of these categories of shifted complexes is also a certain way to see non-rationality. But so that is the classical picture that we want to keep in mind. So let's go to once again. So the homological mirror symmetry here means that to this element of H3 we correspond certain torsion on the Landau-Ginzburg model, and so if you want to play further with the geometry, you can deform this Orbi-Landau-Ginzburg model and then resolve it, and so then you will get a non-trivial element in the corresponding H2 or in the corresponding K group, and so that was conjectured a long time ago. For them, it was proved by Witten and Buffer in 1994, but by now, this paper or in many others, we have a better understanding of what's happening in this algebra geometric setting. So, all right, so that's what we want to understand from algebraic geometry. So we can briefly talk about these examples of Milnor. So what Milnor did is he considered S7, and the way he studied, basically, it was for him, it was nothing else but the S3 bundle over S4. So this is so-called Hopf vibration. And of course, that's true for spheres of many other odd dimensions. And so he starts with this trivial sphere, and then he produces a lot of surgeries. And then this surgery actually produces many different fake spheres, or if you like, exotic spheres, which have different structure than the classical sphere after you apply the surgery. And the invariant that it's used here, it's so-called Kervaire-Milnor invariant. And so the Bordism group of this construction, the different non-smooth structure that you get in such a way, in this case, is just Z28. So that's the classical 60 years ago construction by Milnor, and of course after that this was so there were a lot of masters of surgery which generalized this construction to many other examples. So now what I would like to do is, and this is done in a joint work with Grama and Cavenaghi. Look at this classical construction from the point of view of something I have just erased. So what we're going to do is take S7 and multiply it by S1. So now, obviously, I want to put myself in a little bit more familiar to me situation, so at least the dimension where the reals must be even. if nothing else. So, and now, of course, the first thing we do in this paper is to show that this has a complex structure. And in fact, instead of going Milnor's way, considering this Hopf vibration, we want to put ourselves to something that is closer to algebraic geometry. And so, first theorem is that all S are obtained from the standard one via generalized log transforms. So this is an important part to the studies which come in this topological modular forms. Because the work done by Hopkins, Ravenel, Uri, Berend, fits well with this construction here, but I don't think that I'll need this today so much. All I'm trying to say here is that the classical surgery in the 7-dimensional case, I mean, obviously that's true in other dimensions as well, and that's considered in the paper, is transformed to this generalized log transform. So instead of thinking of classical surgery, we think of these log transforms now, where what we do here, we have represent this thing as a vibration with fiber T4, and then just like here, so we take a neighborhood and we glue it back after a certain then twist, and pretty much if you write the matrix, this is really a log transform by T2 in one direction and by T2 of the other direction. And so these numbers PQ of the log transform precisely correspond to the multipliers of Z28. And so you can get all elements of the Vortism group in terms of this surgery. So I mean, most likely Leonardo will talk about this. But so now what I want to do is really do algebraic geometry and category theory. So I forget about beautiful theory of so remember that Ron Stern was telling me in the time of cyber-Witten invariance that like 50 years ago, knowing well surgery was guaranteeing you a job in topology in top universities in the United States. So then, of course, during the 90s, you really needed to know cyber-Witten theory, and that's what Ron did. But what I want to claim now is that maybe we go back to surgery. It's a beautiful theory, but we try to refresh it a little bit from the point of view of derived categories. And so instead of looking at these maps here, I'll look at a little bit different map. That's why I needed this S1. So these fibrations actually, besides that they satisfy mirror symmetry, but I won't have time to talk about this today. So they have a beautiful algebra geometric interpretation. So 12 of them are actually, so let's denote by H, the Hopf motif, or if like S1 cross S3. So, so this has been, as many of you know, subject of very deep research by Bupercio, Messerman, and K.S. Lee, which started in somewhere in Bulgarian mountains a year and a half ago. But so the theorem says that out of this S1 cross sigma 7, so where sigma 7 is are these exotic Milnor spheres. So 12 of them are fibrations of, so with, so let's denote this by Z. So 12 of them are fibrations over P1 cross P1 with a fiber, this Hopf surface. So they have absolutely the same cohomologies, but categorically they are different. And 16 of them are fibrations by this Hopf surface over P1, sorry, I apologize, P2, but weighted P2, with different weights depending exactly on the slope transform which you perform in order to get this object. So all these things have the same cohomologies, so they are very simple ones, but they are different invariants connected to the this log transforms, which distinguish them, and of course the way to look at this is as I propose. So we think of this as Brouwer-Severi Hopf schemes. So in other words, so these are going to be classified by certain Brouwer group in this case, that's precisely Z28. And so we have different vibrations by in the same way as in this case, we have different vibrations by Pn. So here we have different vibrations by the Hopf surface. And then the classical Kerber-Milnor invariants are nothing else by this Brouwer-Severi schemes, but with fiber not Pn, but the Hopf surface in this case. So basically what I'm saying is that what Milnor did was algebraic geometry, but just not over Pn, but it's the Hopf surface that is the building block of all this. And so now I'll be a little bit more precise in what I'm saying here. So this as I said, there are examples of Brouwer-Severi schemes, but with fibers X1. And so basically what I want to describe to you now is what this derived category look like. So in the first case, in these 12 cases, so we have a derived category of Z looks in the following way. Let me first remind you here that the derived category of P1 cross P1 has 4 exceptional objects. I mean, obviously, the derived category of P1 has 2 exceptional objects, and then the product of this product of these line bundles O and O of 1 over P1. And so this is a vibration over P1 cross P1, and therefore this derived category actually consists of, so deep analytic here, of H, but with twists. So we have 4 exceptional objects here. By this statement here, we have 4 derived analytic categories. That participate in this semi-orthogonal decomposition. And so this was described by a student of Lino, who has been many times here. Her name is Abigail Ward. So now the point here is that actually there is a for each of these species corresponding phantoms. And then you have some other exceptional objects as well, which determine this category. So the Hopf surface is not algebraic, it's not symplectic even, for obvious reasons it doesn't have a second homology group, but still it has a derived category of analytic sheaves described by Abigail, and so no matter that it's complicated, I mean, you can actually spot the presence of some phantoms there. So it is this part that is related to the log transform, which I have mentioned, and so that is the part which measures categorically the elements of the Milnor group that was studied classically. So similarly, we have the same phenomena in the case of the other examples. So where we have these vibrations of Hopf surfaces over this weighted projective P2. So the derived category of weighted P2 has a semi-orthogonal decomposition, which has that many exceptional objects. And in a similar way as before, so here this of course numbers depend on the surgery that we are applying. So you have a semi-orthogonal decomposition in these 16 cases. So you have sheaves on this Hopf surface with the twists as before. And so you have all these semi-orthogonal decompositions of this analytic shifts. So once again, so the point that I'm trying to make here is that this classical Milnor invariants are nothing else but categorical invariant for the category associated with this complex manifolds. Now, this have mirror symmetry, and so they have certain decompositions of atoms, and so this story can be pushed to be connected with this invariant of this classical 7 manifolds, which become invariants of the category that we are trying to study. So of course I'm giving you just the most classical, the most simple example here. All this works for time-dimensional things, like one of the most interesting one is S15 cross S1, so where you can actually get this group is 1614, I believe. It's a rather big group of cobordism in this case. And so that becomes this time of vibration again over this time P weighted P4, but the fibers are products of products of sort of products, but vibrations of products of this of surfaces, and due to the biggest variety of log transforms, with generalized log transforms that you can do here, you actually get bigger variety of bigger variety of examples in this case. All right, to summarize,